Hi, everyone. Welcome back to Bufnagle the podcast, where we explore entertaining and enlightening discussions of the adventure of life and all things good. From science and technology to history and philosophy to leadership and success. We hope to give you a better understanding of the world and skills for everyone to pursue their own adventure.
Hi, everybody, and welcome back to Bufnagle the podcast, where we talk about all things good and the pursuit of the adventure of life. I am Rafe, and I have the distinct pleasure of being joined by Harry again this week. Harry, how are you?
Rafe, I'm doing well. I'm excited to be here. I'm sorry I couldn't make it last week, but I'm excited to learn a little bit more about genealogy in mathematics.
It is an interesting thing, and I don't know if other fields do this, and we will get to some of the details of this on where it all comes from and how it all works out. But first, I have to thank the listeners for being here. We appreciate you being here, and because of you, we are a global top 10% podcast. You can reach us at bufnagle@bufnagle.com. And if you are new to the podcast, thank you for coming. We appreciate having you here. Give us, listen to all the episodes, and then listen to them again and download them to your friends' phones, and then tell us whether or not you like them or not. And then I'm sure you'll come up with a reason to come back. Remember, tell a friend to listen. You will get a free episode, and subscribe. There's a subscribe button somewhere on your phone, somewhere on the app that you're listening to me talk right now. There's a way to subscribe, or what do they call it? Sign up or get notified. There's a thing you can do.
Hit the button, ring the bell.
There you go.
Ring the bell, and we'll let you know that we're live and we're here.
We will send content your way automatically, and it will be real content, not just like a brick through your notification. It won't be a brick through your window, right? All right, so if you want to write us a great review, that'd be awesome. Put that out on the interwebs for people to read. If you have a bad review, then don't just keep it in your head and just let it disappear into the ether.
Yeah, and send us whatever you want. Send us questions. We're here. We're willing to listen to them. Don't send us a brick through our window. But if you do, I'm sure you'd probably throw the brick, with a note attached, through the kitchen where the BlendJet 2 is sitting.
You know what? That reminds me, all this math stuff makes me quite thirsty. And there is nothing that goes better with mathematics and history than a smoothie.
And Bufnagle the podcast, that's right. And I think the best smoothie maker that you can get, the best blender, is the BlendJet 2. It's portable, so you can blend up a smoothie at work, a protein shake at the gym, or even a margarita on the beach. It's small enough to fit in a cup holder, so you can take it in your car, and it's powerful enough to blast through tough ingredients like ice and frozen fruit with ease. It's whisper quiet, so you can make your morning smoothie without waking up the whole house or a mouse. And the last 15 plus blends recharges quickly via USB-C, and best of all, it cleans itself. All you've got to do is blend water with a drop of soap, and you're good to go.
The best thing about the BlendJet 2, other than these great things that you listed, is you can get a BlendJet 2 that reflects who you are. A zillion colors, a million patterns. I think they have more patterns and colors than there are numbers on the number line. They have so many out there. It is unbelievable. So with all these options, the question's got to be, what are you waiting for? Go to blendjet.com, the link in our description, and grab yours today, and be sure to use the promo code BUFNAGLE to get 12% off your order and free 2-day shipping. No other portable blender on the market comes close to the quality, power, and innovation of BlendJet 2. They guarantee you will love it or your money back. Blend anytime, anywhere with the BlendJet 2 portable blender. Go to the link in the description for blendjet.com and use the code BUFNAGLE to get 12% off your order and free 2-day shipping. Shop today and get the best deal ever.
Well, that makes me excited.
Well, right? So last week, your thirst is quenched. Your thirst for smoothies is quenched.
That's right.
But your thirst for knowledge is, I'm sure, is current. That's exactly what I was going to say. Unsatiable.
We're related or something.
Yeah, go figure that. Okay, so we started talking last week about this history of mathematics that can be told in the form of a genealogy. That there were really smart people who got degrees in mathematics, and then they became advisors for other smart people to get degrees. And you can kind of trace that line and build a genealogy of all these really smart people. And we started with the Bernoullis back in the late 1600s, and we worked from the Bernoullis up through Euler, who did stuff with all sorts of modern math that we're doing. We were talking about Lagrange and Laplace, Poisson, Fourier, Dirichlet, Martin Ohm, and then a bunch of other guys in another line those guys got the Lipschitz. But if you start with Menke and some of these other guys, you get to Kastner, Pfaff, and Carl Friedrich Gauss, the man in German mathematics in the early 19th century. And you can run up through Gauss into the guy we stopped with was a guy named Klein. But I've gotten some feedback since that episode, and there's people had a number of questions because there are other advisors of some of these people that I did not mention, right? So sometimes there will be co-advisors. In fact, I had two advisors, and so they each have a line then. So this genealogy can get really branched. And there's a couple interesting things to note. Like we talked about Martin Ohm, whose brother was George Ohm, who is named for whom the unit of resistance in electricity is named. Right? And it turns out that Kastner, the guy who was on the Gauss side, who mentored Pfaff, who mentored Gauss, Kastner was the grandfather of Ohm. Right? Not the real grandfather, but the academic grandfather of Ohm. All right? They go through a guy named Karl von Lansdorff. Right? Lagrange was also an advisor of Fourier. So Fourier had Lagrange and Lagrange did Poisson and Fourier. Okay, talk about a guy like those three guys are super special.
So not only do you have a split from a single going into, I guess I'm going to call it two parents.
Yep.
Right, but you also have a parent with two children.
Yeah, the things get it doesn't make okay. So
this isn't a family tree. This is like a family vine.
It is. It's not even a vine. It's you know what?
Giant bush.
It can be very incestuous, right? In the math sense, right? It's not a well-behaved graph, as they say in mathematics. It splits and loops back on itself, and there's some very complicated
statisticians
things.
aren't genealogists.
No, well, genealogy is pretty easy because everybody has mom and dad.
So one of the real interesting guys, though, is this guy Laplace, who got his degree in 1769. He had his advisor was this French guy that Harry, I can never pronounce these names, these extra letters and these accent marks and stuff. But there's a guy named Jean Laurent d'Alembert. I'm sure that's not Alembert. It looks like Alembert to me. Is probably
just say Alembert. You're an American.
Alembert. 1735. He's credited with the fundamental theorem of algebra, which is sometimes called the D'Alembert Gauss theorem, right? Because Gauss did a similar thing, working in a different place, and that says that you know what a polynomial is, right? If you say ax to the n plus bx to the n minus 1 plus right, all the way, you have x's to powers, right? And you have coefficients in front of them. And you kind of study this in like algebra 2 and stuff like that. But it turns out that essentially, there's some nuances to this. You have to be kind of careful that certain coefficients aren't zero and stuff like that. Mm-hmm. But you get, if you have an nth degree polynomial, you have n roots to that function has n roots. There are
right where the function equals zero.
Yep. Where it goes to zero, right? See, so what you can do is you can write it as x minus root 1 times x minus root 2 times x minus root, and it will multiply out, and you have to just fill in the coefficients, and there you go. So that's his theorem. That's the fundamental theorem of algebra. Go figure, okay? His advisor was a guy named Caron in 1710, then a guy named Varignon in 1687, then a guy named Malebranche, 1672, and before that is a guy named Gottfried Leibniz in 1666. Have you ever heard of Leibniz?
That one's a little familiar.
Yeah, Leibniz, for those of you who took calculus, Leibniz was, he independently of Newton, and gets less credit, discovered the calculus. Right, Leibniz was working in Germany, and Newton was working in England during plague years. And Newton had to do the calculus. It was like, what did you do on your summer vacation? He said, well, he was living in London, and the plague came through, and he said, I'm going to go live with my mom up in the farm there, out in the outskirts of Nowhereville. And he did, and he was studying the motions of the planets and gravity. And he was like, you know what? I don't have enough math to do this. I think I will invent calculus. So that's what Newton did. And Leibniz was doing a very similar thing on the continent. So they both kind of did this. And it's interesting because he chatted with Jacob Bernoulli quite a bit, who we met last week. Mm-hmm. And he's kind of considered an advisor or he considers Jacob Bernoulli his student, even though it wasn't a formal relationship. So these guys are all tied together this way.
So at this point, because the previous episode, as I remember, as our listeners would remember, ended with Klein, right? We were doing genealogy forward in time.
Yes.
Now we're going backwards in time a little bit, right? So now we're back up to Leibniz, right? So we're no longer in 1726.
Yeah, we're 1660 now. We're pushing back, and you can keep going. You can go backward to a guy from one of Leibniz's advisor was a guy named Thomasius in 1643, and Thomasius's advisor was a guy named Friedrich Leibniz, who was the father of Gottfried Leibniz. So, all right, and his was in 1622, and nobody knows who his advisor was. That is a dead end. But it turns out that Friedrich Leibniz was married 3 times in the early 1600s, and his first marriage resulted in 6 children, 2 of whom made it to adulthood, and 4 of them died very early. And his second wife produced no offspring, and then she died. And then his third wife produced a daughter and a son, and that son was Gottfried Leibniz. So in order to get the Leibniz calculus, you had to get Friedrich Leibniz through the first wife, through the second wife, to the third one. This is where it starts. These things start feeling like real human stories at this point when I start reading this, because it's easy to see them on a page in an encyclopedia, and then they invented this or they discovered that or they developed this, but
as if that's the only thing to their entire life.
Exactly, right. So they're doing real life things in the meantime, right? They're going out to dinner, they're going to the store, they're buying new shoes, they're doing things that regular people do, but in the meantime, they're doing these things that reverberate this shaking of the human history story takes place with a little wiggle they did then, and it ripples all the way into where we are right now.
Yeah, it's pretty incredible to think that, we're talking about mathematical genealogy and whose advisor is who and where do these all fit. And I'm sure the listeners at this point realize we are going to step forward again in time very shortly to see where Dr. Rafe Donahue is.
We will.
You've had a human story. Leibniz has a human story. Gauss has a story. Newton has a story. Ohm's got a story. All these people are more than just the scientist.
And that's the thing I think that we tend to miss when we teach these little siloed pieces of history, or these siloed pieces of science, or these siloed pieces of literature, whatever they are. These are very complex individuals, I'm sure, and they had. Some of them were trained as lawyers, and some were trained as philosophers, and some were trained as theologians, and some were blatantly agnostic, and some were devoutly orthodox, and others were a lot of them were Jewish, and some were raging anti-Semites, and they're this massive, diverse pool of individuals that are all linked through this interesting little thing that we can trace, because we know who helped whom get, and I think of it's like a Dr. Seuss book. Is everybody standing on the shoulder, guys behind him, and so this Leibniz thing was interesting, but that end of the genealogy ends with Leibniz's father there, but Gottfried Leibniz had 2 other advisors. One was a guy named Christian Huygens, Huygens, and he was big into telescopes and astronomy. He invented the pendulum clock, which was for centuries the most accurate clock. Before the pendulum clock, Harry, you had candles that they would put
nails in. Yep. And then with a candle, they would time it,
Yep.
right, at a certain timing, probably through like an hourglass type thing, and say, well, when this candle burns to this nail, the nail falls and hits the tray, a certain period of time has passed.
Right, and they would know that if an inch and a half of wax would take however long to burn under standard conditions, and they would put something, I guess I'll call it ringy, underneath the candle, so when the candle burned and the nail fell out, it would go ding onto the thing and it would wake you up. But he did pendulum clocks, and he built this 43-inch telescope in the mid 1600s. And he discovered Saturn's moons, and he determined that the strange shape of Saturn that they were seeing at the time was due to the rings of Saturn. That was him. And this was one of the advisors of Leibniz who did the calculus. But on his other side, he had an advisor named Weigel in 1650. All right. And it goes Weigel, Miller, Mueller, Steinmetz, a guy named von Luchen Reketus, and von Luchen Reketus, his advisor was none other than Nicolas Copernicus in 1499. All right, so Copernicus.
So what you're telling me is that you're gonna tell me next that you were related to Copernicus. Is that right?
You know what? Spoiler alert. Yes, that's where we're going. We're going to, and you can take Copernicus and trace him back to a guy named D. Ferreira, and you can go and you can go back to 1068 AD to a guy named Abu Ali al-Husseinu ibn Sina.
I'm sure you nailed that pronunciation.
If I did, I win something. But in 1068, he's the oldest one I could find in the list. And that's 1,000 years of genealogy in mathematics. And these are, for what it's worth, those tend to be shorter generations. Because a guy will get a degree and then 10 years later will be an offspring, will get a degree sometimes. So you can trace from this Abu Ali al-Hussein ibn Sina up through Copernicus, up to Steinmetz, up to Weigel, to Leibniz, up to Laplace, and then from Laplace up to Poisson, Dirichlet, Lipschitz, up to Klein into 1868.
And where does that lead us then?
Well, before we go any further, there was another question we had. And this question was about Euler and E being a number. We talked a little bit about the square root of -1 being I. And if you square I, you get -1. But the question is, what is E? And it turns out E is considered the base of the natural logarithm. Okay, so here's how to think about this thing. Okay, if I want to multiply 100 by 1,000, right? 100 times 1,000. Well, I can do that. I know how to do that. I take 100 is like 2 zeros, and I take 1,000, which is 3 zeros. I put them together, and I get 100,000, right? But if you want to do that mathematically, what you're going to do is you're going to write 100 as 10 squared, and you're going to write 1,000 as 10 cubed, right? And in order to multiply those together, all you have to do is add the 2 and the 3, and you get 10 to the 5th.
Because we have a common base.
Because they have a common base. So what you can do is, if let's say hypothetically you're working with tens all the time and you're multiplying them all together, and you write everything in base 10 like that, 10 to something. Well, if you want to multiply those numbers together, all you have to do is add the exponents. Okay. Well, there's a function called the logarithm, and what it does is it takes the exponent off and just works for the exponent. So the log base 10 of 100 is 2. Because it just looks at the exponent piece, right? And the log base 10 of 1,000 is 3. So if you want to multiply two numbers with the same base, all you have to do is add the exponents or add the logarithms. Is what you have to do. Okay? Now we just talked about base 10, but you can do the same thing with base 2, right? And you can do it with base 17 or base 3 or whatever you wanted to do with that. Well, there's a thing called the natural base, which is a thing you would never think of. But it comes up in 2 places. It shows up in what's called instantaneously compounded interest. Okay, so let's say that you let's say you're getting interest payment. You have $100, and you're getting, just say, because you happen to be a very lucky man, you're getting 12% interest on that annually.
Oh, that sounds great.
Yeah. So what you do is you say, well, I have $100. I have it in the thing. At the end of 1 year, they will say, here, you had your money in here for a year. Here is your $12, and you get $12. All right, because that's 12% annually, compounded annually. But you could say, I don't want you to do it annually. I would like you to do it every 6 months. Okay, I would like you to do it compounded semi-annually. So what they do is they say, well, what we're going to do is we're going to give you half of that interest twice as often. Right? And it seems like, well, that should just be the same. Why would it matter?
It's slightly better.
It's better, right? Because at 6 months, well, you have 6 months of money in there at 12%, but that's not going to earn you the full thing. It's only going to earn you about half of that stuff, right? But the second half of the year, you're going to get interest not only on the principal, but on that little bit of interest that you earned during the first 6 months. Right? That's the power of compounding and compound interest. And that's why when you put your money in the bank, you want to have it, you want to build up, keep that money in there.
You want to compound as often as possible. As often as possible.
So the immediate question comes, okay, so if 6 months, every 6 months is better than every year, why don't I do it monthly and just get 1% every month? And there was like, well, heck, why don't I just do it daily and take 1/30th?
1%.
Why don't I do it every hour or every minute or every second? Why can't I just do instantaneously computed interest? And it turns out a very interesting thing happened. You would think that it would get better and better and better and better. And if you could get the partition smaller and smaller and smaller, you would think that it would become infinite. But it doesn't. All right? It converges to something that's better than simple interest, but not as good as infinity. Okay? And the way you have to get there is this thing. Okay, now you got to, for those of you playing along at home, you might want to get all your bufnagle brand chalkboard, all right, and that wonderful chalk you get from the merch store, all right. So here's the thing that guys like Euler and these other guys figured out. If you take a number, okay, you're gonna take a number. You can take the number 1, and you're gonna add 1/2 to that. So 1 plus 1/2. Which is 1 plus a half.
Yep.
All right. And because you had a 2 in the denominator, we're going to raise that to the second power. Right. So 1 plus 1/2, quantity raised to the second power.
So I'm at 9/4.
9/4. And right. So you get 9/4, which is 2.25.
Yep.
Right. Now I want you to do the same thing, but instead of the 2, you're going to use the 3. So it's going to be 1 plus 1/3 raised to the third power. Okay. So it's whatever that is.
64 over 9.
4/3 to the third. 4/3 to the third power.
64.
Okay? Yeah. All right. So it's 2.37 is what it is, give or take.
Yeah.
Okay. And then you're going to do 1 plus 1/4 to the fourth power. And then 1 plus 1/5 to the fifth power. Right. And then you're going to keep going like that and plug in bigger and bigger numbers into that denominator and the same number into the exponent. Right. So you're doing two competing things here. On one hand, you're adding, every time you go up a step, you're adding a smaller and smaller number. Right? So when you get to 100, you're at 1 plus 1/100, but raised to the 100th power. Right? So 1 plus 1/100 is 1.01. Right? But you're raising that to the 100th power. So you have the competing things that are going on is that piece inside the parentheses, as you get bigger and bigger, is getting smaller and smaller, but it's converging down to 1. It's always bigger than 1.
It will never
always.
Yeah, it will never be less than 1.
Right. And it's never going to be 1. It's always bigger than 1. And what you're going to do is you're going to raise it to higher and higher and higher powers. Right. The other thing that's interesting is so think about if you did each of those things independently. If you just took 1 plus 1/n without the exponent thing, then that thing would go to 1. Right. As the denominator gets bigger. But if you just took 1 plus 1, 1 plus 1/3 or 1 plus 1/10 or something, and raise it to bigger and bigger and bigger powers of n, then that thing would always be bigger than 1. And when you raise it to a gigantic value, it's going to blow up. It's going to always get big. Right? So you have two competing things. One of them is you're shrinking down to 1. And if you took 1 and raised it to the billionth power, you're still going to get 1. But as soon as you get bigger than 1 and you raise it to a power, it should blow up. But since those two things are fighting with each other, you get a very strange convergence. And those two things, like for example, if you use 1 over 100, you get 2.7. If you use 1 over 1,000, you get 2.72. If you use 1 over 10 million, you get 2.71828169, right? And that's very close to the number we call E, which is the base of the natural logarithm, which is 2.71828182. Right? So what will happen when you raise that to bigger and bigger numbers, you converge to this number. It's a wonderful number. It's irrational. It's transcendental. It's a very fascinating number. And it shows up all over the place in mathematics. And then, of course, these crazy guys decided to say, well, let's just stop working with E. Let's raise E to complex numbers. And let's see what happens then.
It wasn't hard enough. And I think for those of us at home,
yes,
with our chalkboard, the chalkboard's full now.
Yes,
because I've got 1 to 100.
Yep.
And all of that, multiplied and then exponentially multiplied. So at the end of the day, so now we have E as the base of the natural log. We know what generally how we can compute E by ourselves if we have a lot of time. So where does that lead us next?
Well, E shows up in a lot of mathematics. Okay, it shows up a lot of times. We talked last week that e to the I theta is cosine theta plus I sine theta. So sines and cosines are related to E, and E and I and pi are all related to each other. So this is like the basic thing upon which the whole math world sits, is on these big pillars there. Okay, so that was the thing. So the question was, where did the base of the natural logarithm come from? That's where it comes from, and it shows up in all sorts of things. But back to Klein. Okay, so Klein was this guy, late 1800s. He did things called game theory. He did number theory, abstract algebra, and he invented. Have you ever heard of Mobius strip, Harry?
Absolutely.
Take a piece of paper, take a long, thin piece of paper, like maybe 2 feet long. Yep. Take 2 feet long and maybe an inch wide. Take a piece of paper. And what you do is you don't make a loop like a watch band. You don't take a loop and make a watch band. What you do is you give it a half twist and then close it back up. And then if you take a piece of a pencil and you try to draw just on one side of that strip, it turns out that strip only has one side. Okay.
Yep.
So it's a Mobius strip. A Klein bottle is a Mobius strip in 3 dimensions.
In 3-dimensional space. Right. So the idea is that if you start on any single point on the Klein bottle, right? Because it's a surface at this point, right? And not a line. If you were to draw a line on this surface, we'll start on the handle. And I'm sure you can pull up a picture of a Klein bottle for the listeners at home. You can go into the handle. The handle will take you inside of the bottle, but the inside of the bottle will take you to the outside of the handle. And then the outside of the handle will take you to the outside of the bottle, which takes you back onto the inside of the handle. So
it's a surface that has only one side. It's like a bottle that has only one side, and it's a 3-dimensional. So that's Klein, okay, and that's one of the things he did, along with game theory, number theory, abstract algebra. Things were getting really crazy in the late 1800s with all the miraculous new mathematics they were coming up with, different algebras. You took algebra in high school and in college probably, but there are other algebras. You may think, well, how can there be another algebras? Well, there are.
Matrix algebra, linear algebra.
Abstract algebra, group theory, number theory. Okay, so all those things are in there, okay? Klein had a student named Lindemann, and Lindemann proved that pi was not only irrational, it was also transcendental.
So what is a transcendental number?
Well, if something is transcendental, if it transcends all the other things, it's better, it's above.
It's like Zeus, but for numbers.
It is up. It's like an enhanced state of numberness. In mathematics, a transcendental number is a real or complex number that is not algebraic. Right? It is not the root of a non-zero polynomial of finite degree with rational coefficients. So most of the stuff we work with is, mathematicians started working with polynomials a lot. X squareds, x to the third, x to the fourth, all that kind of stuff. And they have solutions. They have roots. A transcendental number is not a solution of one of those things. There are numbers that you can't get in solving that.
From a polynomial equation.
with rational coefficients. So if you start with rational coefficients, you'll never land on these transcendental numbers. And it turns out there are zillions of transcendental numbers. In fact, there are more transcendentals and irrationals than there are regular rationals. Right? If you remember, a long time ago, we did some infinity stuff. We talked about countable and non-countable infinities. There are lots of transcendentals. There are lots of irrationals, and they just dwarf the rationals. Most of the world that we live in is these.
It's irrational transcendental.
Yes. There's lots of stuff out there. And the guy who figured that out was this guy, Lindemann's offspring. One of his students named David Hilbert. And Hilbert invented a thing called Hilbert spaces, right? And he is also the inventor of the hotel infinity thing that we talked about when we did those infinity things, right? Way back. Hilbert had a student named Steinhaus, who is credited with the Banach-Steinhaus theorem. Now, he was in Poland in World War II. Right? And this is where this gets interesting from a historical perspective as well. He was a Jew in Poland, and he was not safe working there. So he worked underground. He taught mathematics underground in Poland from memory. Wow. He didn't have any books, and he was a superstar of the Polish math world back in World War II. In 1937, a student of his, Mark Kac, got his degree, and Kac made it out of Poland and made it to Cornell, where he ran into one Richard Feynman at a seminar. And Feynman and Kac started talking. Feynman was giving a seminar, and Kac said, "Yeah, I'm working on that problem too, but I'm working at it from this other angle." And it turns out they converged on the answer, and they met each other in this. It's
like a modern day Newton Leibniz.
But they were friendly.
Yeah.
Newton and Leibniz didn't quite get along with that. But the rest of his family, the rest of Kac's family, was lost to the Nazis in 1942. They were all killed, and Mark Kac got out, and now we have this probability theory. And he went on, did great things there at Cornell eventually, and he had a student named Murray Rosenblatt who did a lot of things with Markov processes and time series. And Murray Rosenblatt had a student named Richard Davis, who was at UCSD at San Diego, and he was actually an All-American in sailing in the NCAA. He was a very, very, very smart guy. He got his degree in 1979. He went to MIT, and he taught at MIT from 79 to 81. And from 81 to 08, he was at Colorado State University and then Columbia. And in 1992, Richard Davis and a guy named Peter Brockwell, who got his degree from Jose Moyal somewhere in Australia, were kind and gentle enough to, how should I say it, to mentor me through the process of getting a degree. And I stand on the shoulders of all of these people. And there is a website called the Mathematics Genealogy Project. And there are 200,000 mathematicians in this database, and they are all linked by their advisors and the students. So if you you can just do a search on Mathematics Genealogy Project, and if you want to, you could look up our friend Copernicus, and you can trace Copernicus through Requitus to Steinmetz to Müller all the way up to me. Now, I don't have any offspring, so that tree will end there. But Richard Davis has a number of offspring who have offspring of their own, who are now begetting students. And I knew a long time ago, probably 15 or 20 years ago, that this mathematical genealogy project was in existence. And I had mapped out what I knew at the time, because this thing was not full. Yep. And every day people add more data. And it is amazing to me that my line stretches back 1,000 years, Harry, to this guy whose name I cannot pronounce, all right, Abu Ali al-Hasune ibn Sina, at least that far back. And I guess they would be first cousins of mine, or cousins once removed, or nieces or nephews are coming out of the Richard Davis line. And I mean, that man was just what do you say, freaking brilliant. I've never met a man that had such command of his mathematics. But he goes back through Murray Rosenblatt and through Mark Kac, who could have been lost to the Nazis.
I think more so than anything else, it's humbling.
It
Right?
is
It's humbling because you can trace this line all the way back through these great individuals, and you think to yourself, "Oh my goodness, am I good
worthy?
enough? Am I worthy?"
And I look back on it, and like in grad school, what I knew then compared to what I know now, it is stunning how much you can learn once you get out.
Yes,
And
you're
that
not
was
confined to an academic institution.
Yeah, that's one way to put it. But what those guys did for me, and what all of these guys did for all of these people that came after them. All right, how Keck advised Rosenblatt, and Steinhaus advised Keck, and Hilbert advised Stein. I mean, these were really brilliant individuals. And that's the thing about Richard. He probably still is he was an all-American sailor. He knew everything about sailing, in addition to being a super genius smart man with regard to time series and stuff. And then Peter Brockwell was this wonderful Australian guy, and he had 3 bikes in his office, Harry. And I was like, "Why do you have 3 bikes?" He says, "Well, sometimes I ride to work and I forget I have my bike here and I walk home." but he was, and I forget, I was listening to some music or I was playing the piano or something like that, and he turns out he's an organist at his church. And he said he likes the organ better than the piano because in the organ you get to use your feet.
Right, because piano's not difficult.
Because it's not hard enough, right? And these guys were just they wrote the time series textbook that we used in the I guess it was late 80s at that time. And the work they have done since then has been off the charts. And the other thing that struck me is how wonderful of people they were. That is, well, they are because I think they're all both still around, and they are. And I think all of this whole list here that goes back 1,000 years has probably the same. Like all of these would say this about their advisors. I'm sure they would. That this human interaction leads to this connected band. Like you talk about the long gray line, and then it's a real thing coming out of West Point. That's a thing, and you track. There's all sorts of things they track with that line, and that goes back to 1803, 1802, and so that's the thing. You can track that, and they have that written down. This goes back 5 times as far. And I'm just, like I said, I am humbled and grateful for what all of these people, all of these guys did, and these are all men. Okay, these are all men because only men got degrees, and that was the state of the world then. But this is getting bigger now and more rich by all the women that are being included now too. So all the things that like this is growing.
Well, and then the stories grow too, right? So you're not just limited to, some guy who's out doing whatever for his normal job and figuring out calculus and time series on the side. You might have the woman who's at home who discovers mathematics while taking care of her children.
Well, there was I read a thing. Do you know what a tessellation is?
Yes.
Okay, a tessellation.
They discovered a new
pentagonal tessellation. Okay, yeah. So there's this a tessellation is a pattern that you repeat that can cover the floor. Okay,
without gaps,
right? No gaps, no overlaps, and it can go infinitely far in each direction. So if you take a square, it's very easy to tile. You can build a tessellation out of a square, and there are lots of different ways you can do it. You can line them all up in rows and columns, or you can just do rows and you can offset the columns. Right?
You can do triangles pretty easy. You can't do circles.
Circles don't work because there's always gaps.
Circles don't work.
Right.
You can do hexagons.
Hexagons work well. Yep. Regular hexagons.
Yes.
All right, but irregular hexagons, I have to say I don't know. But the question is, what about pentagons? And you can build certain pentagons that when you put them together, you can get you can do pentagons. Okay, and there are lots of different pentagons, 5-sided pentagons that can do this. And this one lady, she was a mom, and she studied this stuff in her spare time, and she developed this notational method for how to define a pentagon, right? You can say, well, here's a pentagon, and you say, well, it's a regular pentagon, all the sides are the same, right? And then the angles are the same. But you can have irregular pentagons that have different angles and sides. And she came up with a notation for doing these things. And she discovered through her notational methodology, she was like, well, if I set this equal to this and this, I should be able to get another pentagon that tessellates. And bingo, there she came up with a new one, just like out of nowhere because of her notational technique. And these people come out of nowhere, and she didn't have an advisor. Unfortunately, she's not on the list.
A new line.
But she could start a new line. Somebody's got to she's got to sneak in there and get somebody to have her as an advisor. But it's a wonderful thing, and it's I don't know if the chemists do this sort of thing, or if physicians do this, but it typically has to be one of these things that is I don't know, where you have a distinct advisor and you can track it with a thesis. But I guess I just want to say that I'm just grateful. It was a wonderful discovery when I first found this thing. Somebody showed it to me back about 20 years ago, and the database has gotten monstrously huge now. And go look at it, find your favorite mathematician, and follow his or her progress on the Mathematical Genealogy Project out of I think it's North Dakota State.
Oh, there you go.
So there you are. All right, Harry. That's what I got. That's where we are.
Good. I think it's kind of nerdy. It's kind of exciting. I think it's good for people to remember that it's important to keep record of what you've done, and to never take for granted from where you've come. Right. So you have this lineage. Be humbled by your lineage and continue to do good things.
Yeah, that's the thing to point out. There are some people on here that they are. There's one guy that I was looking up on this because the project tells you their names, and then I would go and I'd look them up. And part of Wikipedia will tell you for some of these guys who their students were, notable students, I think, and then advisors. Some of them have that in the Wikipedia things, but some of them are only known as a stopgap between two other guys. And you know what? Without them, where are we?
Stops. Yep.
And these things interlace with history, like with Leibniz and his mother was his father's third wife, and Keck's family was lost to the Nazis. These are real human stories tied together with a ribbon of math.
One person would put it.
All right, that's what we got this week. Thanks for listening. I hope your gene line proves to be as interesting. All you got to do is tell the stories and write them down. Remember, seek the good, be the good, and spread the good, and enjoy the adventure of life.